Everyone who studies the Fermi Paradox eventually arrives at the same wall. You do the math, you accept the numbers, you acknowledge that a universe this old and this vast almost certainly produced intelligent life somewhere other than here, and then you run headfirst into the same question that has resisted a clean answer for 70 years. If life is out there, and physics says it almost certainly is, then why is the universe so completely, uniformly, persistently quiet? Not slightly quiet, not quiet except for a few tantalizing signals. Quiet in a way that makes silence feel like a physical property of the cosmos itself. Scientists have proposed dozens of explanations. Most of them, if you examine them carefully, come down to three basic claims. Either no one is out there, or everyone is hiding, or everyone is dead. But there is a fourth category of answer, one that gets far less attention than it deserves, for specific, peer-reviewed, published scientific hypotheses that say something completely different. They say the question itself contains a hidden assumption, an assumption so deeply embedded in how we think about advanced intelligence that most people never notice it is there. And once you see it, the silence stops being a mystery and starts being something almost inevitable. Start with the assumption. When most people imagine an advanced alien civilization, they imagine it doing what humans do, but bigger. Building larger structures, sending out more signals, spreading across more star systems, using more energy, becoming more visible. This is the framework that makes the silence feel paradoxical. The more advanced a civilization becomes, the argument goes, the more detectable it should be. So the absence of detection means the absence of advanced civilizations. But this framework contains an assumption that is never examined carefully enough. It assumes that external expansion, outward growth, spreading across space, building bigger things in more places, is what advanced intelligence inevitably does with its capabilities. And for serious scientific proposals, each developed independently by researchers at major institutions, each published in peer-reviewed journals, each taken seriously in astrobiology and SETI research, all converge on the same counterargument. Maybe the direction of development for advanced intelligence is not outward. Maybe it is a direction we have not been looking. The first hypothesis challenges something even more fundamental. Not what advanced civilizations do, but how common the conditions for intelligence actually are. The rare Earth hypothesis, developed in detail by geologist Peter Ward and astronomer Donald Brownlee of the University of Washington, begins with a deceptively simple observation. The existence of complex, multicellular, intelligent life on Earth required not just a habitable planet, but a specific, extraordinary convergence of conditions that compound on each other in ways that make the overall probability far smaller than people intuitively assume. Consider what Earth actually has. A large moon, which stabilizes the planet's axial tilt within a narrow range, and prevents the wild climate swings that would make complex evolutionary development impossible. Plate tectonics, which regulates carbon dioxide levels and prevents runaway greenhouse or icehouse conditions across geological time. A location in what astronomers call the galactic habitable zone. Far enough from the dense, radiation-saturated galactic center to avoid sterilizing events, but not so far into the sparse outer regions that heavy elements needed for planetary complexity are scarce. A Jupiter-sized gas giant in the outer solar system, acting as a gravitational shield, deflecting many of the large impactors that would otherwise have struck Earth far more frequently. A star that is unusually stable in its output, without the flares and radiation bursts that make red dwarf planets far more hostile than they initially appear. Each of these conditions is individually uncommon. Together they form a stack of requirements, so specific that Ward and Brownlee argued intelligent life, not microbial life, but complex intelligent life, may be extraordinarily rare, perhaps unique, perhaps limited to a number so small across the observable universe that the absence of detectable civilizations is simply a reflection of genuine scarcity rather than any kind of silence. The Gaian Bottleneck Hypothesis, developed by astrobiologists Charles Lineweaver and Odisha Chopra at the Australian National University, adds a layer to this picture that makes it even more stark. Their argument begins with a crucial distinction. Getting life started might actually be relatively easy. The chemistry required for the first self-replicating molecules appears to be common throughout the universe, and the early solar system was apparently awash in the organic compounds needed to begin the process. But getting life to survive long enough to become complex is a completely different problem. And here's the specific bottleneck they identified. In the first billion or so years of a planet's life, the conditions are changing rapidly. Volcanic activity, stellar output, planetary cooling, the chemistry of the oceans, all of these are in flux. And for life to survive through this volatile period, it has to do something extraordinarily difficult. It has to actively regulate the planet. It has to consume and produce gases in ways that keep the climate within the narrow range that life itself can tolerate, even as the underlying conditions are pulling the planet toward something lethal. Venus and Mars, they argue, are the more typical outcomes. Early life may have appeared on both, but life failed to exert sufficient influence on the planetary chemistry quickly enough. Venus became a runaway greenhouse. Mars lost its atmosphere. Earth survived because life here, almost accidentally, began reshaping the conditions of the planet at exactly the right pace to stay ahead of the changes threatening to kill it. And the bottleneck is not the origin of life. It is this race. In the early phase, between planetary instability and biological planetary engineering, most planets lose that race. The universe may be full of dead worlds where life began and was extinguished in the first billion years, leaving behind nothing that could ever develop the complexity to become detectable. Now take everything you have just heard and set it against the second major category of hypothesis. Because the rare Earth and Gaian Bottleneck explanations say the silence is real because advanced life is genuinely rare, but the next two hypotheses take the opposite starting point. They assume advanced civilizations do exist. They assume there are minds out there, billions of years older than us, with capabilities we cannot begin to imagine, and they explain the silence by arguing that what those minds are doing is nothing like what we have been looking for. The estivation hypothesis was published in 2017 by Anders Sandberg of the Future of Humanity Institute at Oxford University, along with Stuart Armstrong and Milan Cirkovic. Its title, drawn from a line of H.P. Lovecraft, is both deliberately strange and precisely chosen. Estivation is the biological term for what certain organisms do in extreme heat. They go dormant. They slow down. They reduce their activity to the absolute minimum needed to survive, and they wait for conditions to improve. The hypothesis argues that an advanced civilization with full understanding of physics would recognize something that human civilization is only beginning to appreciate. Computation, the fundamental currency of advanced intelligence, becomes dramatically more efficient as the ambient temperature of the environment decreases, and the universe is not yet cold. The universe is still, in cosmic terms, very hot. The cosmic microwave background radiation, the leftover heat of the Big Bang, currently sits at about 2.7 degrees above absolute zero. That temperature will continue to fall over hundreds of billions of years. And here is the key calculation that drives the hypothesis. Because of something called Landauer's principle, which relates the thermodynamic cost of computation to the temperature of the environment, the amount of useful computation that can be performed with a fixed amount of stored energy scales with the inverse of the ambient temperature. This means that the same resources that allow a civilization to perform a certain number of computations today would allow it to perform 10 to the power of 30 times as many computations if it waited until the universe was far colder than it is now. 10 to the power of 30, a multiplier so large that no comparison to human numbers is meaningful. Under this hypothesis, the most rational thing for an advanced civilization to do is exactly what it looks like nobody is doing. Gather resources, store energy, go dormant. Wait not for decades or centuries, for billions of years, because the payoff on the other end of that wait, in terms of what can be computed and experienced, is so astronomically larger than what is possible now that choosing to stay active in the present universe is equivalent to spending a fortune today to avoid waiting for what would otherwise be an incomprehensible windfall. The silence is not absence, it is patience. And then there is the hypothesis that asks the most fundamental question of all, about what advanced intelligence actually wants. The transcension hypothesis was developed by futurist and researcher John Smart and published in Acta Astronautica in 2012. Its core argument starts from a specific observation about the direction that technological development actually takes. As civilizations advance, their technology does not only expand outward in scale, it simultaneously miniaturizes, densifies, and becomes more efficient at the smallest scales. More computation in less space. More energy extraction from smaller physical systems, more complexity in more compact configurations. Smart argues this is not a coincidence or a design choice. It is a universal developmental trajectory that follows from the underlying physics of computation and intelligence. And if you follow that trajectory forward by billions of years, the destination it converges on is not interstellar megastructures and galaxy-spanning networks of signals. It is the opposite. It is inner space. Increasingly dense, increasingly miniaturized, increasingly self-contained environments of computation and experience that draw intelligence inward rather than outward. Environments that, at their theoretical endpoint, resemble something like a black hole, the most computationally dense, energetically efficient structure that physics allows. Under this hypothesis, advanced civilizations do not go quiet because they are hiding, or sleeping, or dead. They go quiet because they have found something better to do than expand outward into the cold emptiness of interstellar space. They are building inward, optimizing inward, experiencing inward. They have access to more information, more computation, more complexity, in a cubic centimeter of their inner space than we could encounter in a lifetime of interstellar travel. And from the outside, from our position in normal three-dimensional space, with our radio telescopes and our infrared surveys and our search for Dyson spheres, they are completely invisible, not because they are trying to hide, because what they have become no longer intersects with the physical space we are searching. The transcension hypothesis has a specific and testable prediction attached to it. If it is correct, every civilization in the universe should go through a brief window during which it is expanding and detectable, leaking signals in a recognizable pattern, before making the transition to inward development. That window, during which a civilization is visible to a sufficiently sensitive external observer, SMART estimated at approximately 100 to 300 years, against a civilization lifespan that might extend to millions or billions of years. That window is a blink. Finding another civilization during its detectable window would be something like trying to photograph a specific person during the 1 second in their entire life when they happen to be looking directly at your camera from across a crowded city. Not impossible, but so vanishingly unlikely that the absence of a detection tells you almost nothing about how many people are in the city. These four hypotheses do not agree with each other on everything. The rare Earth and Gaian Bottleneck explanations say the universe is genuinely sparse in intelligence. The estivation and transcension hypotheses say it may be full of advanced minds we simply cannot see from where we are looking. But they agree on something more important. They all argue that the question of cosmic silence cannot be answered by assuming that advanced intelligence looks like human intelligence scaled up. The silence, in each of these frameworks, is not a mystery requiring a dark explanation. It is a natural consequence of physics, biology, and the mathematics of development operating at scales of time and energy that are genuinely beyond human intuition. The universe is not quiet because it is empty, or because everyone is dead or hiding. The universe may be quiet because the things in it that are most advanced have moved in a direction that our instruments aimed outward cannot follow. So here's the question that remains. If the estivation hypothesis is correct, the universe is full of sleeping giants, waiting for a future so cold and so distant that the word billion does not come close to describing the timescale. If the transcension hypothesis is correct, there are civilizations computing entire universes of inner experience in spaces too small for our telescopes to detect, indistinguishable from the background physics of reality itself. If rare Earth is correct, we are a statistical miracle, precious in a way that makes our existence the most improbable and therefore most significant fact we know. And if the Gaian bottleneck is correct, the history of this planet is not just the story of life. It is a story of life winning a race it almost certainly was not supposed to win. Any one of these answers would change everything about how we understand our place in the universe. And right now, looking out at a sky that offers us silence in every direction, we have no way to know which one of them, or which combination of them, is true.